Advanced Math, Lesson 96, more double angle identities, triangle area formula, proof of the law of sines, equal angles imply proportional sides. This lesson is kind of a hodgepodge of topics. Mostly we'll be focusing on the double angle identities. We'll talk about the triangle area really quickly. And then this last part, equal angles imply proportional sides, that's more of a, it's kind of an Algebra 2 topic. I'm pretty sure it's something that got taught a long time ago. And I'll look through the lesson again, but I don't think they were adding any new information. Anyways, let's get started with more on double angle identities. So again, these are going to be our trig identity problems. We'll be using rules of the game, and our goal here is to prove that sine of x plus cosine of x squared is equal to 1 plus sine of 2x. So the first thing we can do is, if you remember from the last lesson that we had on this, let's just go ahead and use this exponent or FOIL this. So if I had, well, by foiling I mean sine of x, we should already know this, but you know, who knows? Maybe we forgot. Sine of x plus cosine of x times sine of x plus cosine of x. First times first gives me sine squared of x. Last times last gives me plus cosine squared of x. And then the middle is just going to end up being plus 2 sine times cosine of x. Sorry, sine of x. Oh man, I missed one. Here. Let's write this the correct way. Sine of x cosine of x. There we go. All right. So that's our identity. What this does for us is it gives us sine plus cosine, sine squared of x plus cosine squared of x, which if you remember, these two equal 1. That's one of our identities. So this can just get rewritten as 1 plus 2 sine of x cosine of x. And we have to prove that that's equal to 1 plus sine of 2x, which is great because sine of 2x is one of our double angle identities. Just in case you forgot, we do have our little cheat sheet for our identities. Where is it? Here it is, double angle identities. This one has it written as theta, so we'll go ahead and replace 2 sine of theta cosine of theta, or in our case 2 sine of x cosine of x. We'll replace it with sine 2 of x. So through a little substitution, this now becomes 2 sine of x. So now we have 1 plus, oh whoops, wait, is it 2 sine of x? Hold on, let me, did I do that wrong? Oh, I did do it wrong. Sine of 2x. Ugh. Sine of 2x. Alright, and so then we've proved our trig identity, which equals 1 plus sine of 2x. Cool. So a little bit of foiling, a little bit of substitution using our double angle identity. Let's go to the next one. Hopefully I won't get so tongue-tied on this one. Okay, our next problem. We have cosine to the power of 4x minus sine to the power of 4x over cosine 2x equals 1. Some things we might notice, we can see immediately here, we're going to end up using the difference of two squares theorem. And then down here, we have cosine of 2x, which is great because that's a double angle identity. We may or may not use this. I don't know yet, but before we even look at this, let's simplify this numerator. Let's start factoring that. Let's go to orange this time. So if you remember, difference of two squares makes this numerator turn into cosine squared of x minus sine squared of x times cosine squared of x plus sine squared of x. And cosine squared of x, sine squared of x is a great thing because we should all be memorizing by now that this is equal to 1. So this just becomes number 1. Cool. And then this left side, guess what we're going to do again? Difference of two squares theorem. So that's going to become, wait, actually, is there something else I could do here? Hold on. I think there's something else I can do here. Maybe I don't want to factor it. Let's rewrite this as a whole actually, instead of factoring immediately. Let's see what we're working with. So this is now over the denominator cosine 2x. So now I have cosine squared x minus sine squared x over cosine of 2x. Man, okay, I'm going to look up the cosine of 2x theory. Can't remember anything this morning, and let's see what that one is. Cosine of 2x is cosine squared minus sine squared. So we will be substituting this bottom one. This is just going to equal cosine squared of x minus sine squared of x, and then that's going to be over cosine squared of x minus sine squared of x, and that makes this equal to 1. So we have finished proving our identity. because same number over itself. Okay, so that's it for double angle identities. Watch out for those cosines of cosine of 2x's, and then we should probably work on memorizing these identities because I don't have them memorized. So cosine squared of x minus sine squared of x is equal to cosine of 2x, and then 2 sine of x cosine of x is equal to sine of 2x. So, but then again, you still have your trig cheat sheet because it's a lot to keep in your brain. Now, let's go on to the triangle area formula. So the triangle area formula, actually I'm going to pause and draw some triangles before we go into this. Okay, I've drawn this beautiful, beautiful scalene triangle. And we notice it is neither right nor isosceles. It's not a special triangle. It's just scalene triangle. Let's go ahead and label it. We'll make this, why did the book do that? Okay, so we have A, B, and C. And to find the area of this triangle, we would obviously have to figure out the height, right? So the triangle area formula is that you can find the area of any triangle by multiplying two sides. In this case, I'm going to choose B and C. So the area of any triangle would be like two sides being multiplied. So B times C. And then I'm also going to multiply that by the sine of this angle. So we'll call this, what am I going to label these angles? We'll label them X, Y, Z, right? So B times C times the sine of Y. And that will give us the area of this triangle. Now, the reason why is because if we need to figure out this height or this sine of Y, what we'd have to do is we'd take the hypotenuse of C and we'd multiply it by the sine of Y to get the height, right? So that's where we have C sine of Y, right? And then, so this we can think of as being the height times the base. Oh, whoops, last thing, we got to take all of this and divide it by 2. And that will give us the area of any triangle. So the thing we can do this logically and we can always solve for the height every single time, but it does become useful and fast to have this formula and knowledge of the formula. So the way this works is the angle that I use always has to be in between the two sides. So another way I can do this would be A times B times the sine of X. I can say A times B times the sine of X divided by 2, and that would also equal the area. The other way I could do this is I could do C times A times the sine of Z, right? And it works. So, and then divided by 2. So this is just the quick triangle area formula. They do this because it's quick and it helps you solve these problems faster, which can be very useful if you just turn it into a formula as opposed to doing it the logical way where you solve for the height of the triangle. So keep an eye out for these. Again, you don't have to memorize these formulas. It is useful. There's no test that's going to ask you what is this formula, but it is, it's very, very time saving, which is what makes it valuable. Because I mean, logically we could solve for the height of the triangle, but in the end we're just going to be doing, all the heights would just be these sections anyway, right? So that's that. Last thing we're going to talk about is equal angles imply proportional sides. This is like the concept of a scale factor. Got some similar triangles on the back of this page. All right, so we have two similar triangles here. I believe they're right triangles, but it doesn't really matter. The point here is that if we have A, B, and C, and then we have A prime, B prime, C prime, the ratio of one side to the other will be the same for all of these pieces of the triangle. So if I go from small to big and I take C divided by C prime, that is going to equal the exact same ratio as A divided by A prime and B divided by B prime. So they're all going to have the exact same ratio. This is something in the past that we referred to as a scale factor. Now the interesting thing about scale factors is they're like one-way streets. So this scale factor would only be for the small triangle to the big. If we want to go from the big to the small triangle, we'd have to invert the ratio, which would give us a different scale factor. Again, I don't think I need to do this on the lesson because this is something we learned way back in Algebra 2. And I'm looking at it again. This is the only thing they seem to be talking about. Yeah, they're just talking about this constant of a scale factor. that would, it's whatever ratio this side is to this side. So if I had this scale factor, I could take A, multiply it by the scale factor, and come out with A prime. If I inverted it and I had the other scale factor, like if I had A prime over A, I could take B prime times that scale factor and find out what B is. So that's it. That's it for this lesson. If you guys have any questions, let me know on the school website, and I'll see you in class.